For question 6.29, one type of sunburn occurs on exposure to UV light of a wavelength in vicinity of 300 nanometers. So what is the energy of a photon of this wavelength? So again, we're asked for energy, so the first equation that should pop into our head, because we're not given a quantum number, is energy equals Planck's constant times frequency, and because we're given a wavelength, the other equation that should immediately pop in our head is the speed of light times frequency, or speed of light equals frequency times wavelength. And again, before we can do anything for this calculation, right, because the speed of light is in meters per second and we're given nanometers, we need to convert. Remember that 1 meter is 1 times 10 to the 9th nanometers. So nanometers cancels out, and our wavelength should equal 3.0 times 10 to the minus 7 meters. Once we have our wavelength, we can then find frequency by rearranging that equation, speed of light divided by wavelength. Frequency equals 3 times 10 to the 8th meters per second divided by 3 times 10 to the minus 7 meters is our wavelength. So meters cancel out and we're left with the units for frequency that make sense. We're left with 1 times 10 to the 15 inverse seconds for our frequency. Now that we have frequency, we can then find the energy. Energy equals Planck's constant, 6.626 times 10 to the minus 34th joules per second times the frequency we just calculated, 1 times 10 to the 15 inverse seconds, right? So seconds cancel out, which makes sense because we want energy in joules. So the energy of a photon at this wavelength should equal about 6.62 times 10 to the minus 19 joules. So what's the energy of a mole of these photons, right? Well, what is a mole of anything, right? 1 mole equals Avogadro's number, which is 6.022 times 10 to the 23rd, objects or items, right? We're talking about moles. That's our version of a chemist's dozen. So we know that in 1 photon, there's 6.62 times 10 to the minus 19 joules. In 1 photon, and we know that we want moles, and 1 mole is going to have 6.022 times 10 to the 23rd photons in it. So photons cancel out, and we're left with joules per mole. We multiply 6.62 times 10 to the minus 19 by 6.022 times 10 to the 23rd to get approximately 3.99 times 10 to the 5th joules per mole of photons. So this is joules per mole, so that would be that. If they just asked for a specific energy of 1 mole, then we would just say 3.99 times 10 to the 5th joules. Now, right, the next part people got stuck on, so these UV photons can break chemical bonds in your skin and cause a sunburn, a form of radiation damage. If this 300 nanometer radiation provides exactly the energy to break an average chemical bond in the skin, so that's basically saying the energy of 1 photon, 6.62 times 10 to the minus 19, can break 1 chemical bond. So that basically says that the energy of the photon equals the energy of the chemical bond. So if that's the case, then the mole and energy of 1 mole of photons should also equal the energy to break a mole of these bonds. And that's what this is asking, the energy per mole. And so the only thing is here, it's asking it in kilojoules. Here we calculated it in joules, so divide by 1,000 because 1 kilojoule equals 1,000 joules. And so the answer should be something on the order of 399 kilojoules per mole.